Usually when we think about capturing a moment in time, we just imagine that familiar, that click of a camera shutter.
Right,
Or
exactly.
like a water balloon pops, a bird takes flight, the shutter clicks, and reality is neatly frozen for you to just examine. It's binary, it happened, and we caught it.
Yeah, and it gives us this wonderful illusion of absolute control over time. We just naturally assume that if an event occurs, no matter how brief it is, the solution is simply, well, engineering a faster mechanical shutter.
Right, just build a faster click. But then you step into the world of ultra-fast optical physics, and suddenly that comforting click of the shutter is, I mean, it's a complete joke.
Oh, totally. A complete joke.
Because we are looking at a landscape of time that is so impossibly brief that human perception and really just traditional mechanics, they just hit a brick wall. So, welcome to the deep dive. I've been buried in some incredibly dense optical physics literature lately for you all.
Some really heavy reading.
Yeah, including textbook excerpts on coded optical imaging, an article called Frozen in Flight, and a couple of highly technical papers on ultrafast coded imaging. And today's mission is pulling from all of that to figure out how scientists are breaking the fundamental limits of cameras to freeze light right in flight.
Which is just a huge paradigm shift. I
Yeah,
mean, we are looking at a complete reimagining of what a camera even is.
exactly.
The math in these sources is, frankly, heavy. It involves complex algorithms and deep optical theory, but the underlying mechanisms are just fascinating.
And we are here to extract those mind-bending aha moments without the overwhelm, right? Because we aren't just talking about cameras that shoot thousands of frames per second. We are talking about hundreds of billions of frames per second.
Billions, with a B.
Right. And we're going to explore how scientists are using single pixel detectors, algorithmic reconstruction, and amazingly cheap, humble fiber optic cables to film things that happen in a trillionth of a second.
It's wild. But to understand how they do that, we really have to start with why a normal camera fails.
Okay, set the stage for us.
So the physical barrier that standard high-speed video hits is rooted in the Nyquist-Shannon sampling theorem.
The classic bottleneck.
Exactly. Essentially, this theorem dictates the sampling rate you need to accurately reproduce a signal. In traditional photography, your sensor needs time to register light photons, convert them into an electronic signal, read that data out to memory, and then clear the sensor for the very next frame.
So there's this literal physical traffic jam of data happening.
Precisely. Electronic sensors just cannot read out data fast enough.
Right. So when you are trying to film a femtosecond laser pulse giving across a room where light travels just a fraction of a millimeter in the time frame, you're trying to capture the sheer speed of that event vastly exceeds the capacity of any electronic shutter.
Right. The electrons moving through the camera's circuitry physically cannot keep up with the photons bouncing off the subject. To the human eye and to normal cameras, it's just a phantom streak.
It's just a blur. So how do we fix it?
Well, that bottleneck forces a radical shift in thinking. If electronics are too slow, you basically have to manipulate the light itself. And this leads to the first major conceptual leap in the papers, which is chirped spectral mapping, ultrafast photography.
Okay, CSMUP. This is the breakthrough reaching hundreds of billions of frames per second, right?
That's the one. It relies on a mechanism called time stretching, which builds directly on the 2018 Nobel Prize-winning concept involving ultra-short laser pulses.
Oh, wow.
Yeah, the core physics here utilizes group velocity dispersion, or GVD.
Okay, let's unpack this because group velocity dispersion sounds intense.
It does.
So if I'm understanding this correctly based on the reading, instead of trying to open and close a mechanical shutter incredibly fast, we are taking a broadband flash of light and we are stretching it out in time like a rubber band.
Yes, exactly like a rubber band.
And then using a prism-like effect to map time onto the color spectrum.
What's fascinating here is that you've got it perfectly. When that broadband pulse enters a dispersive material, the different wavelengths, the colors, experience different refractive indices.
So they travel at different speeds.
Right. So you create this rigorous one-to-one correspondence between a specific fraction of a nanosecond and a specific wavelength or color.
That's brilliant.
It really is. By the time that single brief flash of light exits the material, it has been physically strung out. The blue light illuminates the very beginning of the event, then the green, then the red at the end.
So a single snapshot suddenly captures a full slow-motion sequence of frames, just color-coded.
Exactly. Time physically becomes color.
Okay, so we have the speed, that solves the shutter limit. And this is where the sources take a really interesting turn. What if the thing we are trying to film at billions of frames per second is completely transparent?
Ah, right. The invisibility problem.
Yeah, because most of these critical ultrafast events, like a shockwave or the plasma spark, they are invisible.
They are. And traditional cameras only capture intensity, which is just another word for brightness. If a transparent shock wave passes in front of the lens, the camera records absolutely nothing happening.
Because there's no shadow.
Right. And to solve this, the researchers introduced CSCMUI.
Oh boy, the acronyms.
I know, bear with me. It stands for Single Shot Intensity and Phase-Sensitive Compressive Sensing-Based Coherent Modulation Ultrafast Imaging.
We are definitely not saying that whole thing again.
Deal. But the key there is that it captures both intensity and phase.
Right, and to give a visual for you listening, intensity is like looking at the shadow of a glass of water. It just tells you something is blocking the light. But phase imaging is like seeing the microscopic ripples, the morphology, and the actual thickness of the glass itself, right?
That's a perfect analogy. Phase imaging measures the actual delay of the light wave. Even a transparent object slows light down a tiny fraction. By capturing that microscopic delay, we see structural details that intensity alone is entirely blind to.
But the crux of this acronym, the really important part, is the single shot aspect.
Yes, absolutely crucial.
Why is doing it in one single burst so critical here?
Because traditional phase imaging requires multiple measurements. You have to bounce light off a target, take a reading, alter the setup, take another reading, and compare them.
Which takes time.
Exactly. And that causes massive systematic errors. It is utterly useless for capturing non-repeatable, one-off chaotic events like an exploding crystal. By the time you take your second measurement, the event is over.
Right, you can't ask an explosion to pause while you change the lighting.
You really can't.
Yeah.
So CSCMUI grabs both phase and intensity in one single burst.
And there's this specific experiment in the sources that proves this, the E-shape experiment.
Oh, the E-shaped laser pulse, yes.
Yeah, the scientists actually created a nanosecond laser pulse shaped physically like the letter E, and they filmed it.
And because they had that single-shot capability, they capture the spatial movement of this E from the lower left to the upper right corner over nanoseconds.
Which is mind-blowing.
It is. It revealed the hidden multi-mode output and mode competition of the laser. Basically, they were watching the invisible internal turbulence of the laser beam in real time.
And the precision they achieved, I mean, I have to mention the numbers because they are staggering.
They really are.
The sources cite a spatial resolution of 13.92 micrometers and a phase error of just 0.057 radians.
Right.
To be off by a fraction of a radian when measuring an explosion at 1 billion frames a second, how do they even reconstruct that cleanly?
They use a specialized algorithm called PNP-DIP, which stands for Plug-and-Play Deep Image Prior. It iteratively bounces between physical optical models and deep learning networks to clean up the data.
Wait a second. This brings up a massive logical pushback.
Okay, let's hear it.
If we are shooting billions of frames per second and capturing both intensity and phase data for every single frame, plus running complex PNP-DIP algorithms, wouldn't that generate like terabits of data in a millisecond?
Oh, easily.
It would instantly melt a standard computer processor. How do we even store this information as it's happening?
That is the big data bottleneck. And the solution is a mathematical framework called compressive sensing, or CS.
Okay.
It beats the Nyquist-Shannon limit by compressing the data at the exact moment of acquisition. It takes advantage of the fact that most images are what we call sparse.
Meaning they have a lot of redundant info, like a big blue sky.
Exactly. You don't need to measure every single pixel if the algorithm already understands the underlying pattern. But to do this, you have to scramble the incoming light with a spatial pattern generator before it hits the sensor.
And this leads to what I think is the craziest part of the sources. Here's where it gets really interesting.
I know where you're going with this.
Yeah, because traditionally, labs use these expensive digital micromirror devices, or DMDs, to create those random patterns, right?
Right, which are physical microchips with tiny moving mirrors.
But the UFO IMF paper outlines something totally different. Instead of a highly engineered, expensive chip, scientists are using a humble, cheap strand of multimode fiber optic glass.
It's just brilliant architectural chaos. When light travels through a multi-mode fiber, it bounces off the internal walls, taking different paths. And when it exits, It creates what are called all-optical random speckle patterns.
So it scrambles the light naturally.
Yes. And because this happens without any physical moving parts, it happens at the speed of the laser itself. It hits a 10 gigahertz bandwidth. That is vaulting 6 to 7 orders of magnitude faster than electronic pattern generators.
Okay, but I have to push back here. How can random chaos be reliable for scientific imaging? I mean, if it's just random speckles, how does the algorithm know what it's looking at?
That's a very fair question. The thing is, these speckle patterns are mathematically ideal. They boast a wonderfully low correlation value of 0.074.
Meaning they are highly distinct from one another.
Exactly. The algorithm can tell them apart easily. Plus, they are incredibly stable. Even after 6 hours of continuous use, they maintain a correlation value above 0.95. The fiber optic basically creates a consistent, reliable fingerprint for the light.
And this enables the ultimate magic trick of this whole section.
The single pixel.
Yes. Because of the fiber optic spatial encoding and the compressive sensing, they are achieving compression ratios between like 35 and 68%.
Which is massive.
It is so massive that the system can reconstruct a high-resolution 2D image, like the 50 by 50 or 27 by 27 pixel targets they mention, using literally a single pixel detector.
Right, just one pixel. Instead of millions of pixels taking a snapshot, one single pixel just rapidly measures a fluctuating stream of brightness. And the algorithm reconstructs the 2D scene from that 1D data stream.
It's basically magic.
It's just very, very good math.
So what does this all mean? We have these godlike camera powers now, single pixel detectors, cheap fiber optics. What do the scientists actually point this camera at?
Well, the sources point to a very practical target, indium tin oxide, or ITO thin films.
Right, and for you listening, ITO is the transparent conductor used in almost every single smartphone screen on Earth.
Exactly. So understanding how it breaks is highly relevant. They describe a laser ablation experiment, basically using a strong pump laser to destroy the film and a weaker probe laser to film the destruction.
Using the single-shot phase system we just talked about.
Exactly.
So what did the phase imaging actually show that normal intensity imaging missed?
Well, the intensity imaging just showed the material darkening as it failed. The relative transmittance dropped to about 0.58.
Pretty standard.
Right. But the phase images revealed something incredible. They showed an abrupt phase change at -2 nanoseconds relative to the peak intensity of the pump laser.
Wait, -2 nanoseconds?
Yes.
So that proves pre-pulse dynamics.
Exactly. Plasma begins to form, and the material literally starts breaking down before the laser even reaches its maximum power.
That is such an aha moment. I mean, this hidden prehistory of destruction was completely invisible to human science before this.
Completely invisible, because the material still looked transparent to normal cameras. But seeing this early breakdown is absolutely essential for the future of precision manufacturing. You have to know when the material actually starts reacting.
Wow. So to synthesize this whole journey for you listening, we moved from struggling with the physical speed of electronic shutters to literally stretching time with lasers. And then capturing the invisible ripples of light, compressing massive amounts of data with single pixel fiber optic hacks, and finally witnessing the hidden prehistory of an exploding smartphone screen.
It really paints the bigger picture here. Ultrafast imaging is no longer a race to click a shutter the fastest.
Not at all.
It's about the total, holistic capture of information intensity, phase, spectrum, all within a single, unified burst. The concept of instantaneous is no longer a limit. It's just a sequence of events we can finally watch in slow motion.
It's a total paradigm shift. And it leaves me with this final, lingering question to ponder.
Oh, let's hear it.
If coded optical imaging revealed that a laser strike actually begins destroying a material nanoseconds before its peak impact, what other instantaneous events in our universe have hidden prehistories that we completely misunderstand?
Oh, that's deep.
Right. I mean, from chemical reactions in our own bodies to the cosmic forces in the stars, what else are we missing simply because we haven't had the eyes to see it yet?